Now I just want to show you very quickly how to read the results of um, the shell itself. So if I come to, for example, this one, coming to XY, and then come to here for shell, you can see what we have here. So there are few options here, so you can choose the load combinations you want. If you're using envelope, then you have envelope max or min, or you are in steps. Then you can choose if you want automatic control range or you want a user defined control ratios. You can give the maximum and minimum of the numbers you want to see. So if you want to see any part, for example, is over stress, for example, for a stress along this direction more than say 5 MPa, you can limit it to 5 MPa here, from 0 to 5 MPa, and then you can see if there is any tensile stress more than 5 MPa is here or not, because the color would be different. Likewise, for stress averaging, there are two ways: either not doing anything, or over object and group, or at all joints. So that's give you a smoother contour to see. Also here you have resultant force, shell stress, shell strain, and shell layer stress and layer strain, and also concrete design. We will go through it in our next module, but currently strain is just showing the strain of the element inside the shell element you have, but we're mainly focusing on resultant force and shell stress. Resultant force shows the internal forces in the shell element, and shell stress show you the stresses. So let's have a look at them one by one. I just need to explain you how you use these components and what do they mean. So if I zoom here and then I show you the local axis of area. Okay, now I can explain you what do they mean. So F11 means internal forces along axis 1 at the edge of the element. So F11 is compression or tension for this face and this face. F22 is compression and tension for these two faces. F12 is shear along all four edges. M11 and M22 and M12, they are out of plane moment, and V13, V23 are out of plane shear. Then you have the maximum and minimum as also for all of them, which is not in any specific direction. It just gives you the maximum values. So M11 is moment along one direction, but is not based on right hand rule. So M11 is not actually in this way. M11 is along the element, so the moment you can see in this way, and M22 is in the other way, and V13 is shear along these two edges, which is edge 1 and actually axis 3. So it's a vertical shear out of plane in these two areas. V23 is the shear out of plane for these two edges. So let's have a look at the number. For example, F11. If I apply currently, okay, these numbers are 0, so we cannot see this one here. Even earthquake doesn't show you because you have rigid diaphragm. But let's go for M. So you can see the moment is changing in this direction. Can you see? So here you have, when you reach to the beam, you have negative moment, and then you come to positive moment. So your moment is playing in this way. So this is M11 because this is the moment along grid 1. So it's not based on right hand rule. Actually, based on right hand rule, you should say M22. So the moment is in this direction. M22 is moment in the other direction. So you can see it's changed now. So here you have negative and positive and again negative. So moment in this direction. This is M22. And also V13 is shear for this side. So if I zoom out a little bit, so V1 is along these two edges, and from top to bottom actually is from out of plane, so it's in Z direction. And V2 3 is the other way. So this is along these two edges, which is normal to axis 2 and normal to the plane which is out of plane. So you can see the numbers changing from negative to positive. Depends on which side of the beam you are. You are at the midspan or close to the support. So you need to work on this. I understand it's not something that I can show everything in just one small model for you. I just try to find another element to show you a little bit better. So if I select here in group my basement walls, select, and then show selection only and go to 3D. So we will have this part. So we don't have too much shear here, so let's see which one. So V23, so V23 is shear on top and bottom, so you don't have it too much. V13, here you can see some differences, V13, and then because you have soil pressure, then you have M22 and M11 also, so you can see a little bit change. M22 means moment in this direction, and M11 is moment in this direction. So depends on the numbers, you may be able to see something. I think the best area you can see something considerable probably are piles. So I'm coming here, show all, and let's just back to deform shape, and then move down to piles here. And here, if I come here and for example show you M11 and M22, you would be more clear what's going on. So I'm coming for example for these piles, and then I'm checking M11. You can clearly see the moment coming. Here is the column, so the moment is positive. You come to the pause, moments become negative. So this is the way that moments move. Yeah, so this is along 1, and the same for 2 2. You see the other way, but because you don't have support here, you don't see that kind of regular arrangement that we saw. But here you can see the moment here is negative and then going to positive. So that's how it works. And shear likewise what I said. And you have the same for stress. If you come here, you have S11, S22, S12, S13, S23. These two are shear stress. Those are in plane stress. So S11, if I apply here and change this one to Newton millimeter, so here that should be negative stress, and coming to here it's a positive stress. So depends on face you are looking at. Visible face here is top face. So for top face, when you have moment, positive moment here, actually top face is under pressure, bottom face is under tension. But when you come to the support, because the moment is negative, top face is under tension and bottom face is under compression. So that's why you see here, if I choose top face, you will see the same result, it wouldn't be changed. But if I change this one to bottom face, then you will see a different number. So here is positive, here is negative, it's changed. So this is for S11. Again, S22, it's not very clear here. Probably if we go down to the for the lift, it gives you a better idea. Yep, here if I zoom, so here you can see that this is bottom face. We have 4 piles here, so this middle one is for bottom face is under compression. Why is under compression? Because there is no load here at the middle, so these areas are settling more, so you can see a little bit compression here. If I come to top face, you can see tension here. So that means this span a little bit hugging and coming up, and this areas is going down, and this is shear stress. So you guys just need to play around a little bit and have a look at the numbers and have some examples for yourself, then you would be more clear. It's very hard to explain everything in just one simple model. Okay, just one more thing I would like to show you and wrap up this session is showing the forces in pile and also the pile reactions. So if I come here in XY and move down, so here is Z 7000 minus 10,000, so this is the lowest, so this is based on millimeters. So if I back to kilonewton and meter, so here I have my piles. So what I can do, just to show you more clearly, I'm just selecting the piles, and this lift is fine, and we're coming selecting foundation as well, and then show selection only and 3D. So this is what I have for my foundation system. So let's see what do we have here. So how can I check the joint reactions? I need to come here to joints and select my load combinations, for example CombUG2, and then apply, and it gives me the numbers. So if I want to see any of them, I need to come here on the joint and right click on that, and I can see, for example, 1354 kilonewton is the reaction of this joint. Or if I use tabulator, I can see the numbers here. If I want to make it more clear, the best way is coming to the plane and go down to the pile. This is the area that I can see the loads. So this is the pile reactions, 1440, 1447. Yeah, but when we come here, you can see 1000 kilonewton. That's why this column with 2 piles is settling less, because it's strong, and we don't need it actually, because the other piles are taking the same load, so they are settling more, but this is not. And if I come here and zoom for the area that I had lift, you can see the numbers are pretty small, so 122 kilonewton. Okay, probably we need to check the load transferring to the lift, because we have just one span miss in terms of the weight, so that shouldn't be that much difference. Probably loads are not being transferred to the wall. Again, we need to do all those troubleshootings, but sometimes it's long and we cannot accommodate everything in one short video like that. I'm just showing you the errors. Just you need to be mindful that you need to track everything, you need to check everything and show it's correct. We saw this abnormal internal forces in frame, top frame. We realized that this is due to difference in settlement of the foundation around the lift and the lift itself, and now we can clearly see that lift is taking 10% of the load comparing to others. It could be mistake in meshing the foundation, it could be mistake in meshing the wall to transfer load to the wall. We just need to find it. We discuss about all of them together, guys. So you just need to do the same for your job. If there is any question you have, if there is any challenging issue coming up that you couldn't figure it out, I'm quite happy to help you. Just let's compare the result of pile internal forces with this to see if they are consistent or not. So if I come here and select just pile sections, and then show selection only, now I have my piles. So I just need to find one of them and compare, for example, this pile. So this is this joint, you can see here. So this is 1268. If I come here and use frame com UG2 and axial forces, then apply. Let's check the number. So this pile was this one, and if I come here and move, you can see 1260, and when you're going to the end, 1268 almost. And the next one is 120, just you can see 120 here. You can come to fill diaphragm to have a better idea about the compression and tension. If it's tension, the color is blue. If it's compression, the color is red. And currently all piles are under compression. If I come and choose wind and apply, then you see, for example, piles are under tension, some of them are under compression. So this is wind XP. That means pile in one side is under compression and the other side under tension. So if I use this on wind XP, you can see these numbers are changing. Some parts are less under tension, some parts more. Why this governs? Because we have uplift roof wind load, so that uplift governs the lateral upward and downward load. But again, you see the difference. So some areas is a combination of that tension for roof, but the compression due to overturning moment, so this is less, but here is more. So the load transformation is correct. Guys, this is the end of this video. We have one more video. In that video I would like to share with you how to use section cut, how to use the table for checking the output, and also how to utilize modal analysis for normalizing your earthquake load, and some basic information about modal analysis as well.